All right, another kinematics practice problem. This one is on page 53, number 1. So it says, in 1986, the first flight around the globe without a single refueling was completed. The aircraft's average speed was 186 kilometers per hour. If the airplane landed at this speed and accelerated at negative 1.5 meters per second squared, how long did it take for the airplane to stop? So just like I did before, we're going to go ahead and do this both graphically and algebraically. Let's go ahead and take a look at what we know to start. It says that the average speed of the aircraft was 186 kilometers per hour. It says that it accelerated at a rate of negative 1.5 meters per second squared. How long did it take for the airplane to stop? So that's a key word to us. That key is going to tell us that it means that the final velocity is 0 meters per second. We got to remember that. And the question is asking, how long did it take? So that is going to tell us that we're looking for a time. Okay, so looking at this problem, I think we're good to go. We just need to do some graphing. So the graphical approach, we're going to do velocity on the y-axis, as we have been doing, and time on the x-axis. Now, every time we do velocity, we always write it in meters per second. We look at the acceleration, it's in meters per second squared. So I don't know if any alarm bells went off in your head when I was reading, but this does say 186 kilometers per hour. Now remember, I told you that we're not going to have any of these on the test, but it's a good skill to have. So we are going to go ahead and do the conversion here. So 186 kilometers per hour, we need to make that into meters per second. So as you all have those skills now, I just want to remind you that we're going to put the kilometers on the bottom. We're going to put the meters on the top, 1,000 meters in a kilometer, and then also converting from hours to seconds. So 1 hour is 3,600 seconds. And we can go ahead and convert that initial velocity from 186 kilometers per hour to, I got 51 point, I think it's 66 repeating, but I'm going to go ahead and say that as 51.7 meters per second. So that's how fast it starts. So let's go ahead and graph that. So at time equals 0, we're starting at 51.7 meters per second, okay? And after some amount of time, that's our question mark, we're going to have a velocity of 0. So this one's a little bit like one of the ones we did in the practice, okay, where we don't really know. In the one that we did in the practice, though, we just counted down. I don't know if you remember, we went down 2 over 1, down 2 over 1 a bunch of times. I don't really want to count down 2 over, or down 1.5 over 1 a bunch of times to get from 51 to 0. So I'm going to show you a little bit of a different approach. We are given the slope. We know that the slope of this line is negative 1.5 meters per second squared. We know the initial velocity, so we know the change in velocity, which really means, friends, because remember that acceleration is the slope of the line, we know the rise, don't we? We know the rise, we know the slope, and really what we're trying to figure out is that time, which is the run when it comes to our slope equations. So we're just going to plug this in. We can do this, no problem. So we're going to say that slope equals rise over run. And let's plug in some numbers. So we know that the slope is negative 1.5 meters per second squared. We know that the rise is negative 51.7 meters. Why is it negative? Because we're going down, right? The slope is negative, so we know that we're going down 51.7 meters over some amount of time. So if you weren't sure, meters per second, there, because we know that the time can't be negative, so we've got to do that. So now if we take a look here and we solve, we're just going to multiply by t on both sides, and then divide by negative 1.5 on both sides. Divide by negative 1.5 meters per second squared. Our t's are going to cancel there. That's going to cancel out. And we'll find out that our time, the time it takes for that aircraft to come to a stop is, I got 34.5 seconds or so. I think maybe I rounded up there, which is what the answer says it is. Okay, so that's a graphical approach. Okay, again, didn't have to write out givens. That's all good. But if that equation-based approach makes more sense to you, let's go ahead and do that. So we're going to start out with our givens. And again, you don't have to do both. I just want you to be very comfortable with one. And honestly, if you want to do one sometimes and one the other time, that's okay too. All right, I need to go back up here so I can actually see my givens. So I know that the initial velocity was 186 kilometers per hour. We already did that conversion, so I'm not going to do it again, but it's 51.7 meters per second. We know that the final velocity was 0. It says the acceleration is negative 1.5 meters per second squared. And the thing that I'm looking for is time. All right, so now I'm going to go back to my equations. Remember, we had all that list of equations that we were trying to figure out. So we've got initial velocity, final velocity, acceleration, and time. If you think carefully, then the thing we don't care about, we don't know, we don't want to know is displacement. So we're going to take a look at our chart. We're going to look at the thing that has all 3 or all 4 of those, no displacement, and it looks like to be equation 2. So that's the VF equals VI plus AT. This is actually, just in case you didn't see it before, this is actually just a restatement of the thing that we've known for a long time. That's really just acceleration is equal to change in velocity over time. Shh, don't tell. Or you can tell. It's okay. It's a good thing to know. All right, so we're going to go ahead and write that equation down. So we've got VF is equal to VI plus AT. Okay, or again, you can start with the A on the other side. Either way, it's all good. And then we're going to solve that for T. So I'm going to subtract my VF from both sides, or excuse me, my VI from both sides. So I've got VF minus VI is equal to AT. And then I want to get T all by itself, so I'm going to divide by an A, divide by A, and then I can plug in my values. So it looks like I've got a VF of 0 minus, excuse me, it shouldn't be negative, should be 51.7 meters per second, divided by negative 1.5 meters per second squared. And then again, we can do that division and we get 34.5 seconds. Okay, same answer. And honestly, again, just pointing this out to you, it's the same algebra, the same math that we're doing, just a different setup.